Now let us in today's class let us consider um, the next problem. In the last class we were discussing three different problems, and all of them I think were related to particle in infinite square potential, right? Now we will look at harmonic oscillator. Okay, we will apply different types of perturbation on harmonic potential. This is also very important, just like that particle in infinite square potential. These are all one-dimensional systems. So particle in a box problem is the simplest problem that you can encounter in quantum mechanics. And what happens when different types of perturbations are acting on that? That is a class of problems. So we discussed some, and I will give you some more assignments on that. Now a second class of problems are related to this linear harmonic oscillator. What happens when different types of perturbations are acting on a linear harmonic oscillator? So let us start with this one, fourth problem. Let me give a title, linear harmonic oscillator, for this one. So why I am giving this title is, the reason for giving this title is, in this particular problem we will look at linear harmonic oscillator. We will apply a potential to linear harmonic oscillator which is exactly like the usual potential of linear harmonic oscillator. What is the usual potential of linear harmonic oscillator? Usual potential in linear harmonic oscillator is this one, parabolic potential, half kx square, where k is the force constant. Now we will apply a perturbation something like this, something like half b x square, where b is some constant. So you can see that the perturbation is just like harmonic oscillator potential. So it is very clear that when you add a potential of this type to the already present linear harmonic oscillator potential, you can combine these two and you can write it as half into k plus b x square. Okay, so this is exactly like a linear harmonic oscillator potential with the force constant k replaced by k plus b. So that is exactly solvable using either Dirac method or using Schrodinger method. You can solve it and you can get exact solutions. So basically this is not we cannot say that this is a perturbation. This is usual harmonic oscillator potential itself, but we will treat this additional potential as a perturbation and we will apply the method of time independent perturbation theory. So using perturbation theory we will derive the let us say first order correction in energy, second order correction in energy, and we will also compare these results obtained by approximation methods with the exact result. Okay, but naturally we can expect that this problem is basically linear harmonic oscillator problem. Potential does not change the perturbation does not change the potential. So naturally we can expect that in this particular perturbation the approximation method will give you the exact result, just as we have seen in the case of applying a constant perturbation. Okay, so approximation method should give you the exact result. So that is what we are going to do here. Okay, so I will define the problem in this way. Suppose in a linear harmonic oscillator the force constant k changes to some 1 plus epsilon times k. Okay, so I am trying to define this problem in a different way, slightly different way. So k changes to 1 plus epsilon times k. So maybe you can say k changes to a k prime which is equal to 1 plus epsilon times k. So you can say k prime is equal to k plus some epsilon k. Okay, you can see that you can see that this b is nothing but epsilon k. Okay, for example, if you combine them, you will the new force constant will be k plus b. So instead of taking k plus b, I am just taking, if you open this bracket, k plus epsilon k. So b is nothing but epsilon k. Okay, we will see that. So let us say the force constant of a linear harmonic oscillator increases by a small amount. it becomes more rigid. The oscillator becomes more rigid. Then we need to calculate, okay, calculate the exact values, not approximate, exact values of energy. We need to calculate the exact values of energy by the method is by expanding we can say omega as a power series in epsilon. What is omega here? If you remember the expression for linear harmonic oscillator, omega is square root of k by m. Okay, so if k changes, omega also will change. You can express omega as a function of epsilon. So expand omega as a from power series in epsilon, and you get the exact values of energy. This is one problem we want to find. We want to do. Second is using time independent perturbation theory. Using time independent perturbation theory, calculate the first order correction in energy of the nth state and compare. Compare with the exact value obtained here, obtained in part A. Okay, then third step is using again time independent perturbation theory, calculate the second order correction in energy and compare with the exact value. Okay, since this particular potential does not require perturbation theory, exact calculation is possible. Naturally, we should guess that, we should expect that whatever you obtain by the approximation method should match with the exact method here and here. Okay, let us see whether it happens. Okay, so let us do the first part. So what are the energy values of a linear harmonic oscillator? We know that n plus half x cross omega, where n is 0, 1, 2, etc. The quantum number starts with 0. So that the ground state energy is half x cross omega. And omega is root of k by m. K is force constant, m is the mass of the oscillator. Now, so let us call this E and 0, energy values of unperturbed oscillator. Now, when this perturbation happens, let us treat this change in force constant as a perturbation. Okay, so we are not doing a perturbation in the first part. Okay, let us say. Okay, still I am using this notation. E and 0 is the old energy values. So, let us say we want to calculate the exact energy values when force constant changes. Okay, so we can say when force constant changes, omega also changes to, let us say, omega prime, which is equal to square root of k prime by m, where k prime is the new force constant. So let us substitute square root of 1 plus epsilon into k divided by m. Okay, in this square root of k by m is the old frequency, so omega prime is equal to omega into square root of 1 plus epsilon, which I can write as 1 plus epsilon all raised to half. So now you have obtained the new frequency. Therefore, what are the new energy values? The new energy values are En is equal to, if this is En 0, this is En, is again n plus half x cross omega prime. Instead of omega, we have omega prime. And what is this omega prime? N plus half x cross omega into 1 plus epsilon all raised to half. Now we can expand, assume that epsilon is very small compared to 1, a small positive constant. So we can expand this as a power series in epsilon. This is what it was mentioned in the question. So let us do this. N plus half x cross omega. Okay, how do we expand this? 1 plus nx. N is half. Instead of x we have epsilon plus. So next is n into n minus 1 by 1 into 2. So we have n into n minus 1. Half minus 1 is minus half divided by 1 into 2 epsilon square plus etc. Okay, let us find out this expansion only up to second order in epsilon. Okay, so let us write it here. So what are the new energy values? N plus half x cross omega into 1 plus epsilon by 2, and this is minus 2 into 2 4, 4 into 2 8, all in the denominator. So we have minus epsilon square by 8 plus etc. Let us call it equation 1. These are the exact energy values. Okay. So the new energy values will be like n is 0, 1, 2, 3, etc. New energy values will be like this. We know that n plus half x cross omega are old energy values without this change. So old energy values will be modified like this. Right? Okay. So if you open this bracket, multiply with this one, you get old energy values. And this is the first order modification in terms of epsilon. This will be the second order modification in terms of epsilon. Next will be third order modification, etc. But this is exact. These are exact energy values. Now in the second part, so far we have not done any approximation technique. In the second part, what we are going to do is we are going to apply time independent perturbation theory and calculate the first order correction in energy. Okay, we want to see whether this first order correction in energy will be exactly this. Not this, but this term multiplied by this n plus half x cross omega times epsilon by 2. Let us check. Okay. So I will remove this one. Just remember this value expression. Okay. So what is the, consider this change, k prime goes to, for k goes to k prime, which is 1 plus epsilon times k. Consider this change in force constant as a perturbation. So what we need is a perturbing Hamiltonian. Okay. So what is the Hamiltonian, let us say H0, Hamiltonian of the unperturbed oscillator? T square by 2m plus half k x square. Okay, what is the Hamiltonian of the new system after perturbation, total Hamiltonian? It will be p square by 2m plus half k prime x square. Okay, where k prime is, what is k prime? 1 plus epsilon times k x square. Just open this bracket. So we have p square by 2m plus, first term will be half into kx square, that is half kx square, plus second term will be half into epsilon k x square. Now look at this. What is this? This is unperturbed Hamiltonian. Then what will be this? This will be nothing but perturbing Hamiltonian. H prime or V prime. This is the perturbing Hamiltonian. See, this perturbing Hamiltonian is exactly in this form. So half bx square. As I told you before, b is nothing but epsilon k. Okay. Okay, so let us consider this as the perturbing Hamiltonian. Now we have obtained the perturbation. Then we can calculate the first order correction in energy. So what is perturbation? If I write it in this form, V prime is equal to half epsilon k x square. That is the perturbation. So this is part B. What we are discussing is part B. Okay, so first order correction in energy is, as we know, expectation value of the perturbation in the states of the unperturbed system. If you want to calculate the first order correction in energy for the nth state, we have to take the expectation value of the perturbing Hamiltonian in the unperturbed state. Now I am using a slightly different notation here. Earlier I have told you that this ket psi n, okay, this ket psi n 0 is actually equivalent to simply ket n. Okay, this is abstract ket vector. Actually, psi is used as a it's a symbol for wave function, which is the coordinate representation of an abstract ket vector. But for convenience, I have retained it like this ket psi n 0. I have used a slightly improper notation. Let us go back to this original notation. So instead of ket psi n 0, I am going to use this ket n, because in linear harmonic oscillator, in this particular calculation, I will be using Dirac method of linear harmonic oscillator. And in Dirac method, we are more familiar with this type of a notation. Nth state is of a linear harmonic oscillator is represented by as ket n. It's a number representation. Okay. So we will use that. So I will just rewrite this as ket n h prime ket n, or ket n v prime ket n. V prime is nothing but h prime, which is the perturbation. Okay, so let us substitute that. This is perturbation. So n half epsilon k x square n. So this half epsilon k is a constant, n x square n. So basically it is the expectation value of x square in the nth state. We have, in the last semester, we have done this calculation in linear harmonic oscillator in Dirac method in quantum dynamics. Anyway, we will redo it here. Okay, so the first step is to know that the position operator x we can write in terms of creation and annihilation operators, or raising and lowering operators, like this: root of h cross by 2m omega a plus a dagger plus a. A dagger is the raising operator, a is the lowering operator, or creation operator and annihilation operator. So what is x square? X square is square of this term. This is scalar, so h cross by 2m omega. But this is an operator. In particular, a and a dagger are a non-commuting operator, so we cannot simply take a dagger a whole square. We have to operate it twice. So a dagger a into a dagger a. No, sorry, a dagger plus a into a dagger plus a. So the expansion will be this is our expression for En1, and this expansion will be x square is equal to h cross by 2m omega, okay, a dagger square plus a dagger a plus a dagger plus a square. Okay. Now remember, again this we have done in the last semester. A and a dagger, I told you that they are anti-commuting operators, and the commutation relation is this: a comma a dagger is equal to identity. So a dagger minus a dagger equal to identity. That is a dagger is equal to a dagger a plus identity. Okay. So instead of this a dagger, I can change it into a dagger. I can change to a dagger a plus identity plus a square. Okay. And again, this a dagger a is a number operator. Let us say n cap. When it acts on the nth state, you will get n as the eigenvalue. So you have a dagger a here, a dagger a here, 2 a dagger a here. So I can put it as 2n. So h cross by 2m omega a dagger square plus 2n plus I. Let me combine these two, 2n plus I plus a square. This is the expression for x square. So let us come back to the first order correction in energy. Okay, the expression for first order correction in energy was half epsilon k n x square n. Let us substitute the expression for this one, x square. Therefore, what you get is half epsilon k. And if you substitute this, I can take the square terms outside. So h cross by 2m omega. Then there will be 3 terms. Okay, so there will be 3 terms. I will remove this one. The 3 terms are n, first this a dagger square n plus n, then 2n plus I. Both n and I are operators. N is the number operator, I is the identity operator. N plus one more term, n a square n. There are 3 terms. Okay, let's look at the first term. We know that when a dagger operates on ket n, it will go to ket n plus 1. Because a dagger is the raising operator, it will raise an nth state to n plus 1th state with some coefficient. Let's don't worry about the coefficient now. It will go to n plus 1th state. When a dagger operates 2 times, it will go to n plus 2 state. In the bra vector side, you have n vector, vector n, bra vector n. So this bra vector n has to act on and take the inner product with ket n plus 2. So this you will get a term like bra vector n, ket vector n plus 2. Since all these eigenstates are mutually orthogonal, these are 2 different states. Ket n is one state, ket n plus 2 is another state. So if you take inner product, you will get 0. N comma n plus 2, the inner product will be 0. And if you look here, this is a lowering operator, n goes to n minus 1. When a acts on ket n, you will get ket n minus 1. When a acts twice, you will get ket n minus 2. So you have to take the inner product between bra vector n and ket vector n minus 2. Again, they are mutually orthogonal, so you will get 0. Now what you get here, when a number operator, this is an operator, this is also an operator. So when this number operator acts on ket n, you will get n as the eigenvalue. Identity operator, you will not get any eigenvalue is 1, we can say, there is no change. So here what you get is 2n plus 1. When 2n plus I operates on ket n, you get 2n plus 1. 2n plus 1 is a scalar, we can take it outside. What you get is bra vector n, ket vector n, same state, since they are normalized, and that inner product is 1. So this term will yield just 2n plus 1. Okay? So the first order correction in energy is, we can write down the value, En1 is equal to half epsilon. Instead of k, let me write from here, if you take square on both sides, omega square is equal to k by m, so k is equal to m omega square. So I can substitute that value here. Instead of k, we have m omega square, then h cross by 2m omega, right? And this curly bracket will yield 2n plus 1. Okay? So what you get is, m will cancel. I will take a 2 outside from here, so that in order to compare with the exact result. So what you get is, if you take 2 outside, n plus half in the bracket. So this 2 and 1, 2 will cancel, m will cancel, 1 omega will cancel, The remaining things will be half into let's say n plus half into, okay, in this bracket if you take 2 outside you have n plus half. So n plus half into 2 will cancel, m will cancel, 1 omega will cancel. So you have h cross omega. And what is the remaining term? You have an epsilon here and you have a 2 in the denominator. This will be the first order correction energy. Equation 2. N plus half h cross omega multiplied by epsilon by 2. You compare with equation 1. Okay, in equation 1 you have n plus half h cross omega and then a power series in epsilon. 1 plus epsilon by 2. Okay, so the first correction in energy is n plus half h cross omega into epsilon by 2. This is exactly that we have obtained in first order perturbation theory when we apply first order correction energy. So what we see is that this first order correction energy exactly reproduces the correction in energy up to the first power in epsilon, exact value. Now let us go to the second order correction energy. Okay, now we will go to the part C, second order correction energy. Remember the expression summation over m, which is not equal to n, and instead of psi m0 I am using ket n, psi m0 I am using ket m. So we have ket m, this is in terms of bra vector psi m0. Instead of h prime, let me simply use v prime, ket n modulus square divided by, you have to reverse the order, en0 minus em0. This is the second order correction energy. So let us evaluate this first. What is this? M v prime n. Okay, we will look at the square slightly later. Yeah, we can think about, we can calculate the square itself. What is this? Okay, let us see what is this m v prime n. That's equal to m, what is v prime? Half epsilon k x square n. So half epsilon k I can take outside, m x square n, right? Right. Then half epsilon k into, what is that x square? We have done this in the last class. So in the last calculation, h cross by 2m omega. Okay. M a dagger square n. There will be three terms. Right. There will be three terms. M a dagger square n. Then m 2n plus I n, then m a square n. Remember that an important condition, you remember that m is not equal to n. In this summation, m is not equal to n. So m and n are essentially two different states. With this idea, if we look at this, in the first term, when a dagger square acts twice, n goes to n plus 2 states. This is m, but this is a different state. In the previous calculation, here also we have n. That's why we said that you will get inner product n with n plus 2 and this term will be 0. That was done in the previous calculation. But here, m and n are different. So you have an inner product between m and n plus 2, which can be non-zero because m is different from n plus 2. It is possible that m and n plus 2 can be same. So this can be non-zero. Similarly, this also, when a acts twice on n, we will get n minus 2 state. When m has inner product with n minus 2, this can be non-zero because m is different from n minus 2. What about this one? This 2n plus I acts on and we will get 2n plus 1. Okay, so this term will be 2n plus 1 is the eigenvalue when 2n plus I acts on ket. So if that you take outside, you get mn. You have an inner product like this. But remember, m is different from n in this summation. So if m is different from n, this inner product should go to 0. So unlike in the previous calculation in part B, here this term will go to 0. These two terms will be non-zero. So let us look at the non-zero terms more closely. Let us see what we obtain. Okay, let me use here. So what you get, half epsilon k h cross by 2m omega into when A dagger acts on ket. So this result also we have to remember. When A dagger acts on ket, what you get is root of n plus 1 into ket n plus 1. This is the scale factor we will get. Similarly, when A acts on ket n, what you get is root n ket n minus 1. Okay, so if you use that, remember that there is an, I will remove this term. Remember that there is an A dagger square, there is an A square. So what happens to the term A dagger square acting on ket n? When A dagger acts on ket n, you have root of n plus 1 into ket n plus 1. When one more A dagger acts on this one, root n plus 1 is a scalar. So you think about what happens when A dagger acts on ket n plus 1. You will get root n plus 2 into ket n plus 2. Okay. So you have two terms, root n plus 1 into root n plus 2, and you will get ket n plus 2. On the bra vector side, you have bra vector m. Look at the previous term. So what you get here is root of n plus 1 into n plus 2. Okay. Then m n plus 2. The term like this. Plus, this is the result of the first term, ket bra vector m, A dagger square, ket vector. The second term is 0, I told you. Then third term is bra vector m, A square, ket vector m. Here, when A acts on ket vector m, you have root n into ket n minus 1. When A acts twice, when A square is there, then what you get is root n into A acting on, right? When A acts once, you get this. When A acts one more times, root n is a scalar we can take out. Then root n into A acting on n minus 1. Okay, A acting on n minus 1 will give you root n minus 1 into ket n minus 2. So what you get is root of n into n minus 1, n minus 1, n minus 1, m, n minus 2. This is what you get. Okay. Right. Okay, so this term is nothing but a Kronecker delta m comma n plus 2, and this term is nothing but a Kronecker delta m comma n minus 2. Okay. Yeah. So this is about this matrix element, and here we have to take the modulus square of this matrix element. So basically you will be having two terms like this and two more terms like this. When you take the product, what you can show is that there will be actually four terms, but only two non-zero terms will be there. That means which is a product of a term like this into itself. Okay, that means see, there will be two terms like this, and again there will be two other terms. in the square with m and n interchanged. So when you multiply, there will be 4 terms, but in the 4 terms you can write out if you want. You can show that 2 terms will be 0, only in 2 terms will be non-zero, and the non-zero terms will be exactly like this one. Okay, like this one. So basically what you have is the square of this term. Okay, square of this term plus square of this term. The cross terms will go to 0, because the cross terms will involve a term like this into a term like this, and this condition and this condition cannot be simultaneously satisfied. Either summation is over m, so either m is equal to n plus 2 or m is equal to n minus 2. Together it cannot be satisfied. Therefore the cross terms will go to 0. You can explicitly write it down. So En2 is equal to, you have to square it. So squaring it means you will have square of this one. So we have 1 by 4 epsilon square k square h cross square divided by 4 m square omega square, square of this one. So n plus 1 into n plus 2 into delta m comma n plus 2, and there is a summation here. The summation involves m not equal to n. So this term will be non-zero only if m is equal to n plus 2, and in this summation it is possible that m is equal to n plus 2. So when m becomes equal to n plus 2, that term will be 1, right? When m is equal to n plus 2, you have gra vector n plus 2, ket vector n plus 2, and that term will be 1. So this type of a coefficient, and again in the second term this type of a coefficient will come, so that square root will go, and this delta function and similar another delta function will be there. So you have essentially the same delta function. In this summation only one term will remain with m is equal to n plus 2, and that term will be 1. So that summation goes. You have only this term with m is equal to n plus 2. And denominator also you have a term. Put m is equal to n plus 2 here. So E n0 minus E n plus 2 0. M is equal to n plus 2 in this one. Plus then the square of this one. I told you that the cross terms will be 0. Square of this one. Square of this one means the square root will go. So n into n minus 1. And this term is non-zero when summation over m is equal to n minus 2. So when m is equal to n minus 2, this Kronecker delta will become 1 and the summation will go. In the denominator, you have now En0 minus E n minus 2 0. Okay, so this is the thing that we have obtained. Let us simplify. Okay, so En2 is equal to here we can simplify 1 by 4 epsilon square. What is k square? K is equal to m omega square. So k square is m square omega raised to 4. Then you have h cross square divided by 4 m square omega square. Then you have n plus 1 into n plus 2 divided by what is En0 minus En plus 2 0? You remember that the energy levels of harmonic oscillator are n plus half h cross omega. So n is having values 0, 1, 2, 3, etc. So if you put n equal to 0, you get half h cross omega, the first state. N equal to 1, 3 by 2 h cross omega. N equal to 2, 5 by 2 h cross omega, 7 by 2 h cross omega, 9 by 2 h cross omega, like that. So the separation between adjacent levels is h cross omega. Okay, so here we need to take the separation between nth state and n plus 2 state. So if it is n plus 1th state, the difference will be h cross omega. So if it is n plus 2 state, nth state, next state is n plus 1, next state is n plus 2. The separation will be 2h cross omega. But here we are taking, this is smaller than this one. Okay, so when you take the difference, this is a lower energy, this is a higher energy. When you take the difference, what you get is minus 2h cross omega. Okay, plus n into n minus 1 divided by En minus 2. This will be 2h cross omega. This is nth state, this is 2 states below. This is higher, this is lower. So we have 2h cross omega. So here we have minus 2h cross omega here plus 2h cross omega here. So I can take a 2h cross omega outside. So we have 1 by 4 epsilon square m square omega raised to 4 h cross square divided by 4 m square omega square 1 by 2h cross omega. Okay, there is a minus sign here. So this term will be minus. So what is n plus 1 into n plus 2? With all minus sign. So minus n square minus 3n minus 2. That is expansion of n plus 1 into n plus 2 with all minus sign. This minus sign. Plus, this is plus. So we have n square minus n. So this minus n square and plus n square will cancel. Minus 3n and minus n will be minus 4n. So we have minus 4n minus 2. So 1 by 4 epsilon square m square omega raised to 4 h cross square divided by 4 m square omega square 1 by 2 h cross omega. What I said, minus 4n minus 2. I will take a minus 4 outside. So minus 4 into n plus half in order to get this n plus half form. Okay. So finally let us simplify all these things. That En2 is, if you simplify all the terms, what you get is n plus half h cross omega minus epsilon square by 8. Try simplifying all the terms in the previous expression, you will get this. Now this is the, let us call it equation 3. This is the second order correction in energy. Let us compare this with the equation 1. Look at the exact value of energy in terms of the second power in epsilon. What is that? N plus half h cross omega into minus epsilon square by 8. This is exactly that n plus half h cross omega into minus epsilon square by 8. So here also the second order correction energy using the approximation method of time independent perturbation gives you the exact value of energy. And the reason is that we know that the perturbation here, the perturbing Hamiltonian here is simply half epsilon k x square, or of the form some half b x square. It's a harmonic perturbation, not necessarily harmonic perturbation, because harmonic perturbation is something like sine function or cos function. This is a parabolic perturbation, or we can say harmonic oscillator type potential we have applied. So we can combine this with this is essentially like a change in the force constant of the harmonic oscillator. K goes to k plus b, or k goes to 1 plus epsilon times k plus epsilon k, or k into 1 plus epsilon. So we can, that means we can solve it exactly. Okay. See, if an exact solution is possible when you apply a perturbation, then the exact result and the approximation result will give you the same value. We have seen this thing, this type of a situation when you apply a constant perturbation to a system. Okay, this is not a constant perturbation, but this is perturbation is exactly a quadratic term, or a harmonic oscillator potential, parabolic potential. Therefore, exact solution is possible here. So this is how we treat harmonic oscillator, with a quadratic potential, using solving it exactly and also solving by approximation method, time independent perturbation here. In the next problem, let us try something different. Let us slightly change this potential. Instead of a quadratic potential, let us apply a quartic potential. Quartic means x raised to 4, fourth power of x. Okay, that will make our harmonic oscillator an anharmonic oscillator, and we will see what is the change. What is the first order correction energy using this perturbation method.